Hello, and welcome to this episode of Live from NOIRLab at Arizona. I'm your host, Rob Sparks, with our moderator, Jamaica Marshall. Our guest today is Dr. Melissa Brucker from Lunar Planetary Laboratory and the University of Arizona. Melissa's going to tell us about the Spacewatch program, their observatory on Kitt Peak, and their research into asteroids. I'm particularly excited about this episode because it's the first time we featured one of the non-NOIRLab observatories on Kitt Peak. And this will be an occasional series going forward as we'll learn more about some of the other telescopes on Kitt Peak and the research they are doing. First, I'd like to tell you about Kitt Peak National Observatory. Kitt Peak is funded by the National Science Foundation and a NOIRLab facility. It was founded in 1958. It is located about 55 miles southwest of Tucson on land leased from the Tohono Nation. We are indebted to the O'odham for letting us use one of their sacred mountains for astronomical research. Kitt Peak is home to over 24 optical telescopes and 2 radio telescopes. We always like featuring a recent story, and this one is very recent. It just happened today. NOIRLab Stories is our new blog that takes readers behind the scenes at NOIRLab with deep dives into science, technology, and more importantly, the people who are bringing the universe into focus. This blog explores the people and personalities that enable the science and technology of NOIRLab's observatories, including Kitt Peak National Observatory in Arizona, Gemini Observatory on Mauna Kea in Hawaii and Chile, and Cerro Pachon and Cerro Tololo Inter-American Observatory in Chile, and the Vera C. Rubin Observatory as well. And the Community Science and Data Center is in Tucson. So it covers all of NOIRLab's programs and facilities in multiple countries, states, and continents. So, twice monthly NOIRLab Stories brings a compelling human story of science and technology to life through the eyes of people who make it happen. The first NOIRLab story features Amanda Bauer, pictured on the right here. She is with the Rubin Observatory, currently under construction in Chile, building their education public outreach program. And I've known Amanda for a long time, and this is a wonderful profile of her, so I encourage you to check that out. And I believe Jamaica is going to drop that link into the chat so you have it handy so you can look at that. It's a wonderful profile of her. So. Next, I'd like to introduce our guest, Dr. Melissa Brucker. Dr. Brucker got a Master's of Science in 2006 and a PhD in Physics with an emphasis in astronomy in 2009 from the University of Oklahoma. She did her dissertation research at Lowell Observatory in Flagstaff, Arizona, on thermal modeling of Kuiper Belt objects based on data from the Spitzer Space Telescope. Afterward, she was a physics and astronomy lecturer at the University of Nebraska-Lincoln and a near-Earth object postdoctoral fellow at Adler Planetarium in Chicago before joining Spacewatch at the Lunar and Planetary Laboratory at the University of Arizona. Dr. Brucker became the principal investigator of Spacewatch this March. So without any further ado, I'd like to welcome Melissa Brucker, Dr. Brucker, to our thing here, so she can turn on her video at this point. Hi, Melissa. How are you doing today?
Hi, thank you.
Okay.
I'm
I've
doing
turned off
well.
my good. I've turned off my screen sharing, so you can start screen sharing and start your presentation at your leisure.
Okay. Oops, wrong button. Sorry. There we go. Okay, can you see my slides okay?
Yes, sure can.
Great, thank you. As he said, my name is Dr. Brucker, and I am the principal investigator of Spacewatch. I just became the head of Spacewatch last week, so that's pretty exciting. So today I'm going to talk about what we do on Kitt Peak and about our group and what our research is. So first I have this picture of the telescopes that we use on Kitt Peak. Picture is taken from the vantage point of the Mile 4-meter telescope visitors viewing walk. And so you can see in the foreground is the Stewart Observatory Bach 2.3-meter telescope. And we apply for time on this telescope around the full moon so that we can look at objects that otherwise the brightness of the moon would wash away. And then just above the 2.3-meter telescope in this image is the Stewart Observatory 0.9-meter telescope. This telescope, we are the sole users of both the 1.8-meter and the 0.9-meter telescope, and we use them to track near-Earth asteroids. So, the third arrow on the left is pointing to our 1.8 meter telescope dome. This dome looks smaller than the 0.9 meter dome, so I'll cover that in a second. I thought you might be interested in seeing the 0.9 meter telescope up close. So the left-hand picture is a picture of the telescope while it was in the factory in 1921. And this is the original Stewart Observatory telescope from the University of Arizona campus. So the right-hand picture is a picture of the telescope being removed from Stewart Observatory in 1962 in order to be brought up to Kitt Peak and installed on Kitt Peak, where it has been ever since. So the left-hand picture here is what the 0.9 meter telescope looks like today. It's the same body. It's just been painted. And if you can see my cursor, this arch over here is the original declination circle. So the little white dots that you may be able to see represent each represent a degree of declination. And the telescope right now is pointed at 32 degrees declination because of our latitude. The kind of mount that it has is an equatorial mount. This is a pretty standard stable mount. The middle picture shows the front end of the telescope with our mosaic camera. This camera was built by Spacewatch engineers and scientists and was installed around 2002. The very end of the camera that's sticking out is our liquid nitrogen dewar. It's a vessel that holds liquid nitrogen in order to keep our camera cool. And the right-hand picture is looking down into the telescope while the petals of the mirror cover are opening. So what you're seeing in the center of the image is our primary mirror. So this is the 1.8 meter telescope, and you can see it has a completely different mount. This is an altitude azimuth mount. So that means that the telescope moves up and down and around in a circle. So if you look at the bottom here, there are some numbers along the base, and that is representing what direction that is in the circle. And just above those numbers is a circular rail, like a train track. And everything above that rail rotates around. So the entire telescope moves in a circle. At the top, this black cloth here is a wind baffle, so that if it's very windy out, but not so windy that we need to close the dome, then the baffle helps stabilize things. And then we have mirrors. I have arrows over here pointing to the primary mirror cover. So if we were observing, those two semicircles would open up like this. And so the light that we're from the stars and asteroids comes down from the top of the telescope, reflects off of the primary mirror, up to the secondary mirror, and then down into our camera, which is hanging in the upper third of the telescope. Everything is actually black on the telescope. We've just stretched the contrast so that it's easier for you to see the details. Okay, so as I said earlier, I am the principal investigator of Spacewatch, but Spacewatch has actually been around since 1980. It was founded by Professor Tom Garrels and Dr. Bob McMillan at the Lunar and Planetary Lab at the University of Arizona. And its goal at that time was to do surveys of the sky in order to discover small objects in the solar system and to learn about those populations of objects and how the orbits of objects in our solar system have changed over time. So Spacewatch was one of the pioneers of using CCD cameras in order to survey the sky for objects in our solar system. We were the first to measure positions of asteroids with a CCD and to discover an asteroid and a comet with a CCD. Obviously, comets and asteroids had been discovered before, but just with different technology. For those of you who are following some of the NASA asteroid missions, Spacewatch discovered the asteroid Didymos, which is a binary asteroid, and it will be the target of NASA's DART mission, which is a component of the IEDA mission. DART stands for Double Asteroid Redirection Test. So this will be NASA's first planetary defense mission to practice impacting an asteroid. So the DART mission the spacecraft is going to impact the moon of Didymos. And then the asteroid community as a whole will be studying how the orbit of the moon changes after being impacted. We also discovered the near-Earth asteroid 1998 KY26, which will be the second target of the Japanese Space Agency's Hayabusa 2 mission. So we're looking forward to that as well. One of our other previous notable highlights is that during the Wide Field Infrared Survey Explorer mission, it's an infrared space telescope. We made the most follow-up recoveries and measurements of the near-Earth asteroids that were discovered during WISE's cryogenic mission. And also, we have recently participated in 3 International Asteroid Warning Network campaigns. IWAN is a group that was formed on the recommendation of the United Nations to bring together people across the globe to work on planetary defense observations. So in 2017, we took some light curve data of the asteroid 2012 TC4. And in 2019, we took more light curve data of the binary asteroid 1999 KW4. And we're currently part of the campaign to observe Apophis during its flyby, which happened, its closest approach happened earlier this week. And we can talk more about Apophis later if you have questions at the end.
All right, Melissa. This is fascinating. And before you get too deep into Spacewatch and all of the things that you were just giving us little highlights of, little snippets of, we have a question from the chat that goes back to what you were talking about, the telescopes earlier. Mm-hmm. And the question is, why are the telescopes on different types of mounts?
Okay. So the altitude azimuth mount that the 1.8 meter is on, it requires 3 directions of motion. The equatorial mount only has 2 directions of motion. So if you go to a particular angle and just let it, you can have it just go at the rate that the Earth is rotating so that the same stars stay in the field of view over time. It's very stable and it doesn't require intense computing power. So that is, the benefit is that it's stable and easier to operate computer-wise. The alt-az mount of the 1.8 meter does require more computing power. It's why you don't see very many of them that are old, because the technology needed to be developed. In addition, it takes up a lot less space in the building. Because it's mounted directly straight up, the dome only needs to be able to encompass how far it would be if you tipped it sideways. But if you looked at this mount, the telescope can move around a lot. And so it takes up a lot more space in the building.
Those were very clear answers, Melissa. Thank you so much. And one more question. Can you please explain what is behind you, that beautiful image with orbits? I figure it has something to do with what you're going to talk about, your role in Spacewatch. And
so it's actually a lunar calendar.
Ah!
So the full moon is at the top and the new moon is at the bottom, and it's a spiral that goes out throughout the year. So every line in the spiral has a date of the full moon up here, and down here it has the dates of the new moon down here. And then the bright spots that you can see are the ones that have stars are the equinoxes and the solstices.
I have never seen a lunar calendar quite like that, Melissa.
Yeah, awesome. This was designed by Diva Designs for that company.
Oh, excellent. Well, thank you for the awesome description of the calendar, and also for letting us know why we have these different types of mounts for those telescopes. Okay, we're ready to know more about Spacewatch.
Okay, so our primary focus is on near Earth asteroids. Where do they come from? You're probably very familiar with the main asteroid belt between Mars and Jupiter. And on the right-hand side, I grabbed a photo from the internet. I put the URL of where I grabbed it from below. But movies and TV shows often depict the main asteroid belt as all of these rocks floating in space very close together. And that's not actually true. Even though there are millions of asteroids in the asteroid belt, the sheer volume of that area of space is huge. And so they're not close to each other. Every spacecraft that has ever been sent out into the outer solar system has flown directly through the asteroid belt and not hit anything, not even small things. So on the left-hand side, I've shown an overhead view of the asteroid belt, and you can see that a lot of the objects have elliptical orbits they're not too elliptical. They basically stay in this area due to the gravitational pull of Jupiter. And then there are some asteroids out here. These are called Jupiter Trojan asteroids, and in this diagram, Jupiter would be right where my cursor is now. Half of them follow Jupiter in its orbit, and half of them lead Jupiter in its orbit. So they are in the same orbit as Jupiter. And then below, there's a side view. You can see that while most of the asteroids are in the plane of our solar system, some of them do have an inclination to them. So they're not all in this flat pancake of a solar system. So as I said earlier, the main asteroid belt, the asteroids aren't very close to each other, but occasionally, very rarely, they do collide, and then those asteroids might break up into pieces, and some of those pieces might get thrown inward into the solar system, and those are the objects that are the near-Earth asteroids. They are pieces of larger asteroids that are now orbiting closer to the sun than they used to. So I've put here a diagram from the Planetary Society. This montage was created by Emily Lakdawala, and it shows images of all of the small bodies in the solar system that have been visited by spacecraft. So most of these are asteroids. This one right here in the center, Arrokoth, is actually a Kuiper Belt object. It was the second target of the New Horizons mission after it flew by Pluto. And then the 6 objects down here at the bottom, those are all comets. You may be familiar with the asteroids Ryugu and Bennu because they have recently had spacecraft visit them. The asteroid sample from the surface of Ryugu was just brought back to Earth by the Japanese Space Agency's Hayabusa 2 spacecraft, and the NASA spacecraft OSIRIS-REx will be leaving Bennu shortly this year in order to come back to Earth and drop off a sample as well. The OSIRIS-REx mission is actually run out of the Lunar and Planetary Lab, the same department in which I work. So I did bring a 3D printed model of Bennu. You can see that it's sort of spherical, but it has a ridge along the equator here. So all of the asteroids that you can see in this diagram are so small, relatively speaking, compared to planets, that their internal gravity is not strong enough to pull them together to be round or spherical. And so that is one key feature of most near-Earth asteroids, is that they can be weird shaped. So I also brought a model of Eros, which is also figured in this graph here somewhere, I think. Yes, it's this one right here. So this is a JPL model of Eros, and you can see it's very irregularly shaped. And so one of the things that we want to know about is, well, what shape are they and how fast are they rotating? If we learn about how fast they are rotating, it can tell us a little bit about the strength of the object. If it's rotating so really fast, it's possible that it could tear itself apart because the gravity isn't very strong. It's the strength of the material itself that's holding it together. Okay, so the asteroid, the images here, they all look really bright, but that's not the true color of these objects. And so the second montage that Emily Lakdawala created is more of the true color. And you can see that Ryugu and Benno can barely show up in here, and all the comets at the bottom here and asteroid Matilda are very dark. A lot of these objects only reflect about 4% of the sunlight that shines on them. And so they really are black colored. Okay, so more about near-Earth asteroids, which is our main focus. The definition of a near-Earth object is an object whose closest distance to the sun is less than 1.3 times Earth's average distance from the sun. So we call that distance an astronomical unit. So these objects, closest distance to the sun is less than 1.3 AU. Comets can also be near-Earth objects, but they need to have an orbital period around the sun less than 200 years in order to count as a near-Earth object. There's a subset of near-Earth asteroids that are called potentially hazardous objects or potentially hazardous asteroids. Almost all of them are asteroids, but it's technically possible for one to be a comet. In addition to having a perihelion of less than 1.3 AU, they also need to have a specific size range, be in a specific size range. So we talk about the brightness of the asteroid, but a good way to think of it is the approximate size of the asteroid needs to be around 140 meters in size or larger. And they also need to get within a certain distance of Earth's orbit. So the minimum orbit intersection distance with Earth means that the elliptical orbit of the asteroid and the elliptical orbit of the Earth get within 0.05 AU of each other. That does not mean that the object gets within 0.05 AU of the Earth. Only the ellipses that represent their paths get close to each other. Nice and confusing. Some of them actually do get physically closer to the Earth, and we call those virtual impactors. So we can describe every orbit of an object around the sun with 8 parameters, but there's an uncertainty in our knowledge of that. We don't know them to 10 digits of precision, right? We know them to slightly less than that. And so if you create a bunch of model asteroids that their orbits all fall within the uncertainty ranges of the parameters that we know, you have a set of, say, 10,000 or more imaginary asteroids. And a near-Earth asteroid is considered a virtual impactor if one of those thousands and thousands of imaginary asteroids might hit the Earth. So within the next 100 years. So that sounds scary, but the actual probability of an impact by any of these objects is very, very low. It's not something that you need to be worried about. I'm not worried about it, and I look at them every day. But if you want to know more information, I've put a link on there to the CNEOS, which is the JPL Center for Near-Earth Object Studies.
Melissa, yes, we have that link already in the chat, along with a link basically to everything you've pointed out so far. I've tried to keep track because this is also fascinating, and we really want to make sure that everyone in our audience, live and later when they see the chat, definitely have these resources to go to for more information. So thank you for that. And we also have another question if you're ready for one. So you were just giving us some parameters that are used to classify, to determine whether an object will fall into the category of a near Earth object. How was that determined? And I was thinking about this because, of course, we have dwarf planets, right, in the asteroid belt series. And of course, part of the definition, the new definition of what a planet is, moved Pluto down to a dwarf planet from a regular planet. So how do we determine what parameters are used to define near Earth objects?
So asteroids have been being discovered for over 200 years. So our knowledge about them has increased over time, but it's had a long time to build up. If an asteroid is slightly farther out than this definition, it's considered a Mars crosser. And so that's the main quality that makes it different than these near Earth objects, is that their distance and if they might interact with Mars, and if they get further out, they might interact with Jupiter. Jupiter is a powerhouse in the solar system. The sun is 99% of the mass, and Jupiter is 1%, and everything else is in the decimal places. So right. the further out an object goes, the more chance it has to interact with other bodies. Actually, they do separate Earth asteroids into more categories, but it does not affect how we treat them, and it's only due to how close they get to Earth and to the other inner planets.
Oh, okay, but
so it's not scientifically different. It doesn't differentiate the objects or how we would treat them.
Okay,
it's more of a bookkeeping category.
Okay, see, all right, now we're on board. Thank you for giving us a little bit more detail, just because I know people, a lot of people, including myself, when Pluto became recategorized, didn't quite understand how did that happen?
So that's a really funny story. I started my dissertation research at Lowell Observatory, where Pluto was discovered, the week after that vote. And my advisor was the lead Pluto expert there. So I actually didn't see him for several weeks because he was giving so many interviews.
I could imagine so. Wow, that's right. So Lowell Observatory, this is Clyde Tombaugh, right?
Yes.
Right. Oh, wow. I'm glad you connected that for us. All right, Melissa, we're on board. We're on board with you.
So I did want to point out that while there are over 1 million small objects in our solar system that have been discovered so far, well, as of earlier this week, only about 25,360 of them are categorized as near-Earth asteroids. And most of them are small. So here is a chart from the JPL Center for Near-Earth Object Studies, and it shows you how many, the colors represent different size ranges. So in red at the bottom are the number of known near-Earth asteroids that are 1 kilometer in size and larger. And you can see there aren't very many of them. And the middle wedge are near-Earth asteroids that are between 140 meters in size and 1 kilometer. So there are more of those, but the majority of the objects that have been discovered are smaller than 140 meters. And if you consider rocks in space colliding with each other and breaking up into pieces, or if you consider going to a gravel pit, you'll have some really large boulders and then more medium-sized boulders and a lot of pebbles and sand. And that's how the rocks break apart into pieces. There will be a lot more in the smaller size ranges than in the large size ranges. Okay, so why do we care about near-Earth asteroids? Well, there are Earth mining companies that are interested in going to asteroids to mine the resources from them. And near-Earth asteroids get pretty close to Earth and compared to the planets. And so it's a good place to send your astronauts if you want to send astronauts out to space. And of course, they're much easier to send robotic spacecraft to visit as well. But our focus is mainly on the planetary defense side. We do study near-Earth asteroids of both scientific interest and planetary defense interest, but our main thrust is planetary defense. In 2005, the NASA Authorization Act by Congress told NASA that they shall develop, plan, and implement a near-Earth object survey program to detect, track, catalog, and characterize 90% of near-Earth objects that are 140 meters and larger by 2020. Guess what? It's 2021. So there were near-Earth asteroid surveys going on before this, trying to accomplish this goal, but this made it official. Unfortunately, it didn't come with extra funding to NASA. So we have not made that deadline, and we are actually not quite close to it either. Based on population models of how many near-Earth asteroids exist, ones that have been discovered and all the ones that have not been discovered yet, we think that the number of near-Earth objects that are larger than 140 meters in size is about 25,000. So we found 25,000 objects, but those are mostly the smaller ones that don't fall under this mandate definition. So based on this model and how many we've discovered, we think that there are about 13,600 near-Earth objects in the 140 meter to 300 meter size range left to be discovered, and about 1,780 that are between 300 meters and 1 kilometer in size left to be discovered, and 25 that are 1 kilometer and larger left to be discovered. That sounds scary, but it's not, because we have found over 97% of those really large objects, the ones that would be very worrisome if we didn't know where they are, but we know where they are, so we don't need to worry about them. With the current discovery surveys available, so the main near-Earth asteroid discovery surveys right now are the Catalina Sky Survey at the University of Arizona here in the Lunar and Planetary Lab, the Pan-STAR Survey at the University of Hawaii, and the Atlas Survey at the University of Hawaii. And there are other surveys that also contribute to this effort, but those are the main ones. If we consider the work that's going on right now and not adding any telescopes or surveys to that effort, it would take another 30 years for us to meet the congressional mandate that was to be completed in 2020. So what can we do? We need to invest in new, larger telescopes for the purpose of discovering asteroids. And there are two that will be extremely helpful. The Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, will be discovering a lot of near-Earth asteroids. It's not optimized for that purpose, but it will discover them, and it will make a huge impact in this field. In addition, there's the NEOSM, which is the Near Earth Object Surveyor mission, and that will be an infrared space telescope specifically designed to discover near-Earth asteroids using infrared light. So when we look at near-Earth asteroids with our ground-based telescopes, what we're looking at is the sunlight reflected off the surface. What the NEOSM telescope will be looking at from space is the infrared light emitted as heat from the asteroids. So it's a different viewpoint, and you can find darker colored asteroids more easily.
Melissa,
Yes.
can I jump in with a quick question here from our chat? Okay, so we have a question from Michael. Michael asks, obviously he's really enjoying your presentation like we all are, and asks if he could get a copy of your presentation. Is that possible?
I think so. I'll have to make sure I have citations on everything, on all of the images that I grabbed.
Okay, so what I will have, Michael, what you can do is just in the video description, you can always just ask there, and I can post the link after the show when she gives it to us. And also, of course, this will be the recording of this presentation will be available, but definitely leave us a message there, or you can message us on any of our social media channels, and we will connect you with Melissa's presentation when she makes it available for us. Thank you so much. And Melissa, also, just going back to the asteroid surveys that you mentioned Pan-STARRS, of course, with I'm familiar with VRC Rubin, which of course is a program of NSF's NOIRLab, but you also mentioned two more and I missed them. Could you repeat those?
Yes, the other one in Hawaii is ATLAS. I'm sorry, it's an acronym that I don't recall what
Don't worry.
all of the letters stand for. But they currently have 2 telescopes in Hawaii, and they are building 2 more telescopes. I think one of them will be in South Africa, and I'm not sure where the 4th one will be. But they're trying to get global coverage because a lot of the telescopes that we as a community use are in the Western Hemisphere. But if you're trying to catch a really fast moving asteroid that was just discovered, you really want to have coverage all the way around the globe on, in both the Northern and Southern hemispheres and the Eastern and Western, so that there are more eyes and cameras to take data.
Absolutely. Absolutely. Okay. Thank you, Melissa. Thank you. And thank you to everyone in the chat. Keep those comments and questions coming for Melissa here. You have everyone's attention about asteroids, and of course there is a very famous asteroid that we all, I think, know, the impact that it had on our planet and the history of the evolution of life on our planet with the decimation of the dinosaurs with that very large asteroid. And that's confirmed, right? That was an asteroid impact.
Yes. The size of the asteroid that created the Chicxulub impact crater in the Gulf of Mexico was about 10 kilometers in size. So that there's a little arrow here in this chart representing that. As I said, there are very few objects that are large, and the probability of an impact by one of them is over, millions to billions of time scale. So the probability of one of them actually hitting us is extremely, extremely, extremely low. And because these objects are large, if one of them had an unexpected change in its orbit, which we don't think will happen. But if it did, because they're large, they would be reflecting more sunlight and we would see them earlier. We would see them much earlier than we would be able to see a very small asteroid because of the surface area that's reflecting the light. So there's a lot going on in this diagram. But I just wanted to point out this line here is the population, how many objects based on a population model. This diagram is a couple years out of date, so the numbers don't exactly match up to the earlier diagram that I showed you, but or the numbers of how many we expect to still discover. But some of you may be familiar with the asteroid that exploded over the town of Chelyabinsk, Russia in 2013. And that object was 18 meters in size. Now, this diagram says none, but it really means no devastation, not no damage. There was definitely damage. This object was small enough that it exploded in the air. But as it was entering Earth's atmosphere, it was so bright, it looked like a second sun in the sky. And so everyone went to their windows to look out to see what was happening. And when the shockwave of the explosion reached them, it broke all the windows. So if you see, in the extremely unlikely case that you see an incoming meteor fireball, don't be by any windows. It's not a joking matter, but it's some things you just need to think about ahead of time, even though the probability of it happening is minuscule. Some of you may have heard about the Tunguska impact in 1908. That was also in Russia, the country. And it flattened this gigantic forest. So that object, I think, was about 50 meters, estimated to be about 50 meters. There's not a really good written record about it from the time. And so people have done modeling based on the size of the damage area to estimate what size the impactor was. And this also was an object that exploded in the air. So both of them left a lot of meteorites on the ground, but as a solid object did not hit the ground as a solid object. They broke up before they hit the ground.
So, Melissa, quick question here. You, and I appreciate that you clarified that the Chelyabinsk impactor, that it did cause damage, but not devastation. So there is a distinction there. What does devastation mean according to what you use here?
I'm not sure what the official definition would be. The size of the area that was flattened from the Tunguska incident event, it was gigantic. It really was. I kind of think of this as like your city, your county, your state, your continent. If something happened that devastated a whole region, there would still be a global impact. It's if we see this when really large volcanoes erupt, the smoke and the plumes and stuff do make a huge difference. And a very large volcano can change the temperature of the Earth for a couple of years afterwards because of all of the material that has been blown up into the atmosphere. And an asteroid impact could do that too.
Oh, wow. Okay. I didn't realize that. And maybe some people in our audience didn't know that either. And, honestly, there's so much new information we're getting about asteroids. I mean, it wasn't something that as regular people, I think that 20 years ago, we really talked about in like everyday conversation. And now there's a Spacewatch and near Earth objects, like you all are on watch to help make sure our planet is protected. And so we appreciate those extra details that you're giving to us to help us better understand what you and your colleagues do, Melissa.
So this slide is from a Planetary Defense Coordination Office presentation that was given in June of 2019. And the Planetary Defense Coordination Office is a NASA office that, as it says, coordinates. So it not only coordinates with all the observers and the discoverers and the people who characterize asteroids, they also oversee the people who model impacts. So one of the groups is at NASA Ames, and they do computer modeling to see with a bunch of different parameters what would happen if you change the parameters if you're modeling an asteroid coming in and then impacting with the Earth. What are the consequences of changing each parameter? So there is a lot of work in this area going on, and if you want to know more about NASA's role in this, you can visit the URL at the bottom, which is nasa.gov/planetary defense. All of our work is funded through NASA grants that are organized by this program. And they not only coordinate with the scientists who work in this field, but they also coordinate with FEMA, with local governments, with international governments, and lots of layers in our federal government. So there is a disaster plan.
So when we see, in movies and or in our favorite, sci-fi space shows, and they talk about having a defense plan, there actually is one now, for real.
So the very first planetary defense space mission will be is coming up, and it's the DART mission that I mentioned earlier. And it's a kinetic impactor mission. So they're going to have the spacecraft run into the moon and see what happens.
That's incredible. And I did earlier when you first brought up the DART spacecraft, dropped that link in the chat for everyone to find out more on. Thank you, Melissa. You're just broadening our minds to all of the resources that are available to learn more about asteroids.
That brings up another thing I'd like to mention. So while I am a scientist in this field, all of the information that I use to do my job comes from publicly available web pages. I don't have any data advantage over you in learning about these objects. I'm just on more mailing lists than you are.
Oh my gosh. Wait, so the data is publicly available. So how
Yes.
would let's say, I'm an astronomy teacher, high school astronomy teacher, and I'd like to show my students, around the website where some of this data is that approachable for students?
Yes. So the JPL Center for Near Earth Object Studies that I mentioned earlier has a lot of information that you can learn about there, and some introductions. The actual measurements of objects, solar system objects, is overseen by the Minor Planet Center. The Minor Planet Center is basically the clearinghouse of all position measurements of all small bodies in the solar system that people take from across the world. And so they collect these measurements and vet them, and then they update the orbits of the objects based on the new information that comes in. They receive millions of measurements of objects every month. And so we can get a link for their homepage as well. It's the Minor Planet Center.
Got it, Melissa. Dropping it in the chat now.
So what happened this last year? The surveys were still running, but most of the near-Earth asteroid follow-up programs were not able to access their telescope due to pandemic shutdowns. But most of the discovery surveys were kept discovering. And so of all the asteroids that were discovered in 2020, it was actually a record number of near-Earth asteroids were discovered this past year. And 1,425 of them passed closer than 20 times the moon's average distance from the Earth. And 873 of those passed closer than 10 times the moon's average distance from the Earth, from the center of the Earth. And 106 of those passed closer than 1 lunar distance from the center of the Earth. And 9 of them passed at the distance or closer than the geosynchronous satellites. It sounds scary. It's not. None of the satellites have been hit. And all of these objects were very small. All of the ones that passed closer than the geosynchronous satellites were estimated to be less than 12 meters in size.
Okay, so that is good news that none of the satellites were impacted. But if we're thinking about this, out of just in 1 year, we had 9 that came within 12 meters. So, and you pointed out that these are very small, but considering the speed at which they're moving, if they were to impact one of the satellites, for example, would that be categorized as something as destructive or damaging?
I think if one were to hit a satellite, it would, it would, that satellite would no longer work or be in one piece.
Okay.
But as I described with the main asteroid belt, the objects aren't that close to each other. With respect to near Earth asteroids getting this close to Earth, it really does happen all the time. It's not something to be concerned about. This year there were 9. The surveys are getting better at discovering really small, fast-moving objects. And so that's why there are more, you would hear of more now than, say, 5 or 10 years ago. It's not that the amount of asteroids passing close to Earth has changed. It's just that we're better at seeing them.
That makes sense, Melissa. Okay, I was wondering, but it makes sense, of course, as we get better, more advances in technology, that of course we would find out more information than we did before.
Right. So we haven't actually looked at any of the images that we've taken with our telescopes yet. So on the left-hand side, so this is data we were collecting for the asteroid 2008 DB, and we were looking at this asteroid in particular due to scientific reasons. This object might possibly be experiencing non-gravitational forces from the solar wind. And so we want to, the orbit people at the Jet Propulsion Lab are interested in quantifying that amount of thrust that the solar wind is exerting on this object. So on the left side is a full frame image from the 1.8 meter camera. And then I've zoomed in, and the way that we collect enough light from the asteroids, because they are very faint, is we take a series of short images and then we stack them together at the predicted rate of motion of the asteroid. So when we stack the images together in the direction that the asteroid is moving, the sum of the light from the stars makes a trail. But can you see the asteroid in this triplet of stacks? So there are 3 small dots inside this blue oval. So that's the position of the asteroid in this image. So depending on how big your screen is, you may or may not be able to see this, but this is a moderately bright object, and it was right where we expected to be. Sometimes they're not, and that's why we're looking at them. We want to measure the positions, and we try and get 3 stacks so that we get 3 position measurements and then 2 velocity measurements. And with that helps when we submit those measurements to the Minor Planet Center, it helps them and JPL to recalculate the orbits with our information included.
And so the information for these near Earth objects are updated periodically as,
yes.
Okay.
Yeah. So sometimes they're not that easy to see. So what I did to look at this one is I inverted black and white in the images. And then I stretched the contrast of the third image in order to be able to see the last object. So here's the first one where the cursor is there, and here's the second one, and here's the third one. It was very faint in the third pass, in the third stack.
It's incredible that you were able to discern that tiny pinprick there.
When you've looked at several hundred of them, you get pretty good at it. We looked at this object. It was listed on the CNEOS. It's NHATS, and it's Near Earth Human Accessible Target Study. So these are objects where the amount of energy it would take to send a spacecraft there is a reasonable amount, basically.
So something that could
it would be slightly easier to send a spacecraft to these asteroids than to other near-Earth asteroids.
Oh, okay. So you help to define those too for potential future missions. That's really awesome, Melissa. That's fantastic. And I do want to say that we have 3 minutes left. 3 minutes.
On the left here is an image from our Mosaic camera on the 0.9 meter. And we primarily look at just this top half of the center CCD chip here, although we gather information and search for moving objects in the other regions as well. So I've zoomed in on this area right here. And again, I've made stacks of images. So it looks like there are about 6 images per stack in the 3 stacks. So you can see the asteroid really well. It was right where we expected it, and it was bright. So that's awesome. We were able to take 3 really good measurements of the position. Sometimes it's moving really fast. And in this case, you can see that the stars aren't trails. There are 2 separate dots for the stars. So there are 2 images in each stack. And the object was moving so fast that we had to take a shorter exposure time. And the exposure time, the length of time we were taking the image, was shorter than the time it takes to read out all the data from the camera. And that's why there's a gap in between the stars in the star trail. Because there was literally a space in time when we were not exposing the camera. Okay, we also do light curves of objects. So as I said earlier, asteroids are weird shaped. And when they rotate, the amount of light that we see changes. So when an object is facing us, more sunlight is reflected toward us and it looks brighter. And when we're looking at the short side, less light reflects towards us and it looks fainter. So if we take a series of images over time, and then we can plot the change in brightness compared to the other stars in the image, we get a plot that looks like that one that just went off the screen. This is a near-Earth asteroid 2019 EA2. And we took these images that I'm showing you here are from the Bach 2.3 meter on Kitt Peak, but we also use our other 2 telescopes to do this work occasionally as well. In fact, right now we're using the 0.9 meter to take light curve data of Apophis. So the period of this object is actually a very fast rotator. It makes one complete rotation in about 103 seconds. Apophis, its rotation period is 30.4 hours. So there's a wide range in how fast asteroids rotate. How are we doing as Spacewatch, the group? Of the potentially hazardous asteroids, those objects that are larger, whose orbits get close to Earth's orbit. Since we started taking data in 1984, we've submitted over 33,000 measurements of potentially hazardous asteroids. You may notice that the line does not increase in 2020. And that's because we were shut down due to the pandemic from about March 18th to about November 1st last year. But we are back observing again. We are not observing in person yet, but the engineers of Spacewatch and a lot of hard work and extra grant have allowed us to remote control most of the facets that are involved in running telescopes. And so we are currently operating our telescopes from our lab on the University of Arizona campus, and also from a couple of our observers' homes have setups where we can control the telescopes using the computers that we have here in Tucson and also up on Kitt Peak.
Well, thank you so much, Melissa, for giving us insights into how everything that you do with Spacewatch and your research really comes together. And I see, yes, you have one more slide here. And I just wanted to say real quick, because I have people in the chat, were asking again about your presentation, because really, really engaging how they get that and also how they get the links. I will have the links posted in the video description, and I'll make sure to pull those out of her presentation as well. Thank you to Judith.
So I did just want to read some of these acknowledgements out loud. We are very honored to be permitted to conduct our research on Ilocos, which is the Tohono O'odham name of the mountain that we are observing on.
Well,
do you have any quick questions?
Thank you very much. That was awesome. That was great. So near-Earth asteroids are always an interesting topic, aren't they, Jamika?
Yeah, you know, they really, really are. And while we have you here, Melissa, and I apologize for going a minute over, Rob, I know.
That's okay. We're good.
So as you know, when meteoroids are in space, meteors are in space, they're meteors. If they hit the ground, they're meteorites if they're intact, right? Do asteroids have a different name if they impact the Earth?
So the difference between asteroid and meteoroid is size. That's the only difference.
Oh, so are
some people call those smaller objects bolides. If you follow any of the people who are interested in meteors and fireballs, they often refer to the objects as boloids. There's really not a difference between a very small asteroid and a meteoroid. It depends. It's just who's talking about it. So in general, meteoroids are considered much smaller objects, but the near-Earth asteroid community are now discovering asteroids that are 1 to 2 meters, which beforehand I'm sure would have been considered meteoroids. We're just getting better at seeing the small things when they're still in space.
Okay. I'm really glad that you made that distinction, because I think someone mentioned it in the chat earlier, and I meant to ask you. Okay. All right. Size is the difference between those two, asteroids and meteors. Excellent. Thank you to everyone in the chat. And we have, thank you for Melissa. Thank you. Excellent presentation. I learned a lot. Great presentation. So you really captured our interest and our excitement today. Melissa, thank you so much for joining us.
Great. Thank you for having me.
That was great, Melissa. So Jamika, next week is live from NOIRLab at Gemini. Do you have a speaker to announce for that yet?
Yes, Rob, thank you so much. Next week, live from NOIRLab is coming to you here from Hawaii. And our guest is someone who some of you may be familiar with, and that is AAS Press Secretary Rick Feinberg. So join us next Wednesday, 2 p.m. HST, right here for Live from NOIRLab on our YouTube channel. Thank you, Rob, and thank you again, Dr. Melissa Brucker.
Yes, thank you, Melissa. And hopefully maybe, sorry, I think I mispronounced your name at the beginning. Sorry about that. Brucker, Dr. Melissa Brucker. And hopefully maybe I'll be able to get a few years when the DART mission comes to fruition. So I'd love to hear more about that at some point. So that gets closer too.
Absolutely. I believe the impact will occur in 2024. Oh,
super. Yep. I said a few years. That's a few years down the road. So that'd be great. So I think that's going to be a fascinating mission to learn more about. And I love Spacewatch. I've been in this dome on Kit Peak a couple times with one of my friends, Jim Scotty, who works there. And it's a neat facility and does great work. So thank you for joining us and telling us about it. And I'll sign off here. This is Rob Sparks signing off this week. This is live from NOIRLab at Kit Peak.